Okay, hey guys, and welcome back. Yeah, let's do some statistics. So, when we were in the last class, when I saw you guys yesterday, we talked about correlation. And remember that correlation is the relationship of movement between two variables. Correlation does not equal causation. Just because two things move together does not mean that one causes the other, right? Remember the example of my two fingers. Their movement was highly correlated. They were certainly moving back and forth, but not one was not causing the other to move back and forth. Then talked about with correlation, talked about how in statistics we have ways that we can measure correlation, not as an on-off switch, but in terms of a correlation coefficient. The correlation coefficient is a statistic that tells us the extent to which two variables move together. And to show you everything that we need to, let's run a correlation coefficient right now. So the data set that I'm using right here is a data set called states.save. It's available on Blackboard. I'm posting it. And so you probably want to pause right now to make sure you can go download and open the states.save dataset.sav that is on Blackboard. So pausing. Good, we're back. Okay, you have the states.save data set and you have it open. We're going to go up to Analyze. We're going to go down to Correlate. And we're going to go to Bivariate. Always bivariate correlations. All right? Now, in this, I'm going to have WIMLedge and I'm going to have college. Do that. You don't need to mess with anything over here. You just go ahead and you hit OK. Hey, look at this. You should get a table here. All right. The table that came out here, there are two things that we need to look at. The first thing that I always want you to look at, not just with correlation, but with regression analysis that we're going to do today, is statistical significance. And that is the second number. In correlations, it's the sig two-tailed test. Remember, this is our bullshit meter, right? As that number approaches 1, it becomes more likely that the result is bullshit. As it approaches 0, it is more likely that the relationship is real. So statistical significance is the way that we measure the likelihood that our results are due to something real and not due to random chance, sampling error, something like that. All right? Remember that we said in this class, we are going to use the threshold for statistical significance of 0.2 or lower. In other words, as long as this sig two-tailed test is 0.2 or below, we're going to assume that we have a real result. Remember that you can read it in terms of percentages. So if the sig two-tailed test was 0.17, you could say, all right, there's a 17% chance that the result is bullshit. Therefore, there is an 83% chance that we are observing something real. And we figured that for our purposes, 80% real is good enough, or 80 that being 80% sure that we've observed something real is good enough. So therefore, as long as this is 0.2 or lower, that is a statistically significant coefficient. Okay, that's the first thing you do when you run a correlation coefficient. Second thing is you actually look at the correlation coefficient itself. All right? Pearson correlation coefficient is a statistic that ranges from -1 to 1. And the key value is actually 0 in the correlation coefficient. Remember, when two variables have a correlation coefficient of 0, that means that movement of one has absolutely nothing to do with movement of the other. All right? Think about the attendance at class and the price of tea in China, right? Those two things have nothing to do with each other. We wouldn't expect those two variables to move together. All right? As the absolute value of this coefficient increases, as it approaches 1 or -1, values become more strongly related. Remember, negative correlation coefficients can still indicate very strong correlations. The only thing that the negative sign specifies is the direction of the relationship. If things are positively correlated, that means that the direction that they move together. So if we're thinking about my fingers, right? Here's one. Oh, can I get it on the screen? Here's two. Look, these two fingers are moving in the same direction. They have a positive correlation. Negative is when they move in opposite directions. So if you see a negative correlation coefficient, that just means as one thing gets bigger, the other gets smaller. All right? As for the actual strength of the correlation, that's when you look at this number here. Remember that we said correlation coefficients of 0.2 and above indicate very strong correlation. Correlation coefficients of 0.1 to 0.2 indicate strong correlation. And correlation coefficients with absolute value less than 0.1 equals not strong correlation. So you see here, if you've done this right, we have a correlation coefficient between the two variables of 0.58. That's a really high correlation. And it means basically that as the number of people in a state that go to that have a college degree or higher increases, the number of the percent of a state's legislators that are women also goes up. So higher number of people with college degrees, higher number of female legislators. All right? That's the review of Tuesdays. That's how we think about correlation coefficients. Now, correlations are awesome. All right? They can tell us a lot about, oh, don't do that. They can tell us a lot about whether two variables are related. But they do have some shortcomings, right? All we can say from this 0.58 is that these two things are really strongly correlated, right? But we have no idea how much movement of one is associated with movement of the other, okay? So let's say that Virginia in the next 10 years, let's say right now we have 70% of the population has a college degree. Let's say in 10 years, in 2025, 75% of the population will have a college degree. We would like to know, all right, we know that that's going to mean we're going to have a higher percentage of state legislators who are female, okay? But we'd kind of like to know how much more, right? Let's say Virginia has 10% female legislature right now, okay? Well, if we increase the percentage of people who go to college by 5%, how many more legislators are we going to have? How many more female legislators are we going to have? Correlations don't let us specify, in other words, the total effect size of one variable movement to another. All right? The other thing that we cannot do with this method is establish causality. All right? So all we can say here is that these two variables move together. We have no idea if one causes the other, right? And you can imagine, right, that the causal direction here could go either way. Maybe the percentage of the population, maybe if when you go to college and you get more educated, you're more likely to vote for a woman for state office, okay? Or maybe the more women who get in for state office, the more that they're going to pass programs that help with education and get more people through college, right? In other words, we can't establish causality. To start to establish causality, we have to rely on slightly more complicated methods, all right? Complicated, well, I don't want to say complicated, but more sophisticated, that's the right word, okay? I think you're going to see that this method we're going to talk about right now is not necessarily the most complicated thing you've ever seen, all right? And this is multiple regression analysis. All right? What I'm going to do now is I'm going to go into Analyze. Oh, no, I'm not. I lied to you guys. Sorry, I had to look at my link there. I'm going to go to Graphs. I'm going to go to Legacy Dialogues. And I'm going to go to Scatter/Dot. So that's Graphs, Legacy Dialogues, Scatter/Dot. And I'm going to pick Simple Scatter. Very easy, okay? Then I'm going to hit Define. So, hitting Define, in the y-axis, I'm going to put this womb-ledge variable. And then I'm going to take college and put it in the x-axis. All right? Make sure that you have WIM legislature in the, WOM ledge in the y-axis. X-axis is the college variable. When you have that, go on down and hit OK. All right, SPSS thinks, and then, oh, look, it's a pretty picture. Okay? What this pretty picture is showing us is it is showing us every state, right, has a value. I'm going to zoom out a little bit so I can show you this. Or maybe I'm just going to tilt down. Yeah, the tilting down. Oh! Oh my God. Mass destruction everywhere. Okay. Every state has a value for the percent of the population with college or higher. All right? Like this state, whatever the state this is, it looks like they have about 20% of the population with a college degree. They also have a value for the percent of the state legislators who are women. So this looks like a state where about 20% of the people have gone to college and 30% of the legislatures in the state house are female. Okay? You've got a cloud here. We call this cluster of plots a cloud here. All right? You've got a cloud here. Go and let me see if I can do this. Add fit line to total. Then go linear. Why is it not letting me hit apply? All right, anyway. No, because the line's already there. All right. Check it out. SPSS can do this cool thing where it puts a line in there that summarizes this is the line that best summarizes the cloud. Okay? In other words, SPSS goes in and they try to draw a line that is as close to possible from as many points as possible. All right? So they could draw a line like this. Let's say they drew a line up like this. But they drew a line like this point over here would be really far away. They could draw a line like this, right? But then this point would be really far away. And that doesn't seem to capture the basic relationship, right? It seems like if we look at this upward sloping line, this line is a reason. If you had to rely on one line to tell you about all these 50 dots, right? You would think that that this is a pretty good line because it's both not too far from any of the dots. In other words, this line is SPSS draws a line that's as close to the dots as possible. And its slope kind of seems right? Like it seems like this is the general direction of the relationship. Because you can see, right, as you get more and more people who have a college degree, you also seem to be increasing on the female legislature in general. All right? Now, pause while I remount this. Okay, that'll do. All right. Multiple regression analysis basically just tries to fit a line as close as possible to as many dots. That's all you really need to know about the theory of multiple regression analysis. Except that this line ends up looking like a really familiar formula, I will bet. In Algebra 1, I am sure that all of you learned something like this. Y equals mx plus b, the equation for a line. All right? You know it, you see it, you loved it. That is exactly what SPSS has done. All right? They've gone in and they have calculated y equals mx plus b for this entire equation, or for this entire cluster of dots. All right? Now, let's do it in a slightly different format. Let's go to Analyze. Let's go to Regression. And let's go to Linear. Good. All right. In the dependent, please put female legislature. In the independent, college. Don't hit OK yet. All right. All we're doing here is that we are setting up a situation. We are telling SPSS, hey, set up y equals mx plus b for us, okay? Set up basic algebra. In other words, what we're going to end up with, the outcome that we are trying to predict is, remember, called the dependent variable, all right? So the dependent variable becomes our y. We want to predict, the percent of female ledge. Okay? We have an M. We'll deal with M in the second. All right? X is percent with a college degree. We're not gonna worry about the plus B up here, all right? It's really not all that important that we don't have to worry about. Now, let's talk about this M. The M is the slope of the line that we just calculated on that scatter plot, okay? The M is going to be the value that we need to multiply the percent of college in a state. We take the percent of college, we multiply it by M, the slope of the line, and that will equal as close as possible the percentage of female legislators. So, let's go back to SPSS and let's run it. Now, I'm going to scroll down here. Okay, when we're doing regression analysis, I want you to look at three things, okay? First thing that you always look at when you do statistics with me is the standard error, all right? So that means SPSS, when you do regression analysis, splits out three boxes. This is box number one. This is box number three. I'm looking at box number three. I'm going to find percent of population with college or higher. I'm going to look at the standard error. Read it the same way as you read the sig2 tailed test in correlation. So this is 0.19. Well, we know that oh boy, guys, I'm sorry, I'm looking at the wrong thing. Don't look there. look at the measure of statistical significance, okay? Statistical significance, all right? We know that if it's 0.2 or less, it's good enough for us. So this is saying we have a 99.9999% chance of the result being accurate, okay? So good, all right. We know that the result is real. We know that the result is something we can trust. What I want you to look at then, right, is the unstandardized coefficient. The unstandardized coefficient is basically telling us for every one movement of the independent variable, we will have this much movement in the dependent variable. Let me make that easy for you, okay, by using the example. All right, so we have just figured out that the best M for this equation is what? 0.938. I'm taking that directly from SPSS, okay? So what we're basically saying is that we take our 0.938, let's say, let's pick on a state. I'm from Pennsylvania, so we'll pick on Pennsylvania, all right? Let's say Pennsylvania only has 1% that went to college. If we want to know how many female legislators that predicts, we take the 1% in Pennsylvania that went to college and we multiply it by this 0.938. So that means we would expect in Pennsylvania to have, with the 1% in Pennsylvania is going to be associated with 0.938 female legislators in the state house. All right. Now, let's take Virginia. Okay. Let's assume that Virginia, let's go back to my red here. Let's assume that Virginia has 10% female legislators. All right. Then we take the 10% of female legislators that Virginia has. We multiply it by the 0.938. And we say that Virginia, based on the 10% of people that it has in college, that have gone to college, that have college degrees, that we expect them to have 9.38% of a female legislator. In other words, this 0.938 is the effect of a 1 unit move in the independent variable on the dependent variable. Okay? The effect of 1 unit move, the effect of increasing by 1% the percentage of people who went to college. All right? Then you can multiply that by how many units? Whoa. All right. Oh, go away. Go away. Go away. No. Oh, good Lord. Hey guys, I got to stop this anyway because this is starting to go long. It'll take forever to upload. I will come right back with part 2.